let's go back to solving problems. In which case, I gotta change where my camera is. Let's do it. Hopefully that is good enough. Can move this over here. Big. Alright, let's do that for now. Alright, let's get right back into it. Question 2, how to scale your model. We learned all about basic roof lines, estimations of compute and communication, limitations and stuff. So next thing, question 2, integer plus brain float matrix multiplication. In practice, we often do different weights versus activation quantization. What different weight versus activation quantization? So you might store our weights in very low precision, but keep activations and compute in higher precision. Say I want to quantize our weights in integer 8, but keep activations and compute in brain float 16. What batch size do we become compute bound? B is the batch size. Okay, let me think about this a little bit, know exactly what they mean by that. Okay, so the only thing that really changes is rather than doing int 8 times int 8, going from BF to int 8, and then the right. Interesting. So it's the bytes that's changing. The flops should stay basically exactly the same. Let's just write that down. Question 2. This is essentially the same scenario, except the communication bytes loaded changes in the scenario in question 1. We loaded 1 byte per matrix value in what were the matrices called here? In X, B, D, and Y, D, F. Now we're loading 2 bytes per value in, what do they call these matrix? Let's just do BF 16, B, D, and 1 byte per value in int 8 df. Okay. Maybe that will be better. Oh, whoops. Okay. So should be very, very similar to the above. So matrix multiplication, 2df times 2b bytes. So in this, we're loading. So let's say communication bytes equals 2 times BD plus 1 times DF. So it's almost the exact same thing as last time. So we're compute bound when intensity of matrix multiplication is greater than the intensity of TPU, right? We're compute bound when the intensity, when the intensity is greater than TPU, right? Let's assume that for now. Okay. Saturation. Okay. And then floating point operations, flops per second equals 1.97 E14. Floating point ops we actually do equals should be the exact same as before, right? It should be BF times 2D minus 1 which is approximately equal to 2BDF. Nothing changes from previous scenario. Okay. So it's kind of worrying me that they're not saying anything about HBM bandwidth, but maybe the 1.97 was, it's the same thing that I used before. So let's basically repeat what's going on here. So let's say intensity equals 2BDF divided by forgot you have 2BF from writing. So let's say load write. Wonder what the LaTeX generator is going to do about that. Anyway, so we got 2BDF, and below here we've got 2BD plus DF plus 2BF equals, let's do it down here, equals everything divided everything by 2. Actually, let's assume that B is really, really small compared to D and F. It goes 2B df divided by, I wonder if we can still make this assumption because of 2. So we'll write that down. df, assuming 2b is much, much less than d, and 2b is much, much less than f. Okay. So what was their... Yes, b should still be less, but not that much less. Alright, well, let's still make that assumption for now. And the next thing is divide by df, so we get 2b Man, this kind of gets into like the same scenario as the first matrix multiplication though. So I don't know if we really can make that assumption. What batch size do we become compute bound? How does the math work without doing that? Is there a way that we can extract B? Maybe not. Well, we'll figure out what the answer does with assumptions and such. Intensity, the TPU equals 1.97 E14 divided by, same thing, 8.2, right? Is that what they do here? Yeah, 8.2 E11. 0.2 E11, which equals what? 240. Just verify that in Desmos real quick. Desmos scientific 1.97 times 10 to the 14. Answer divided by 8.2 times 10 to the 11. 240, yeah. So with the assumption that 2b is much, much less than d and f, we get a similar result to the B, do they do capital B or no? BF 16 BD times BF 16 DF mat mole results parentheses we become compute bound around 2b is greater than 240. And b is greater than 120. Alright, well, let's see what the answer says, if they validate our assumptions or not. They want something better. Yeah, it's the same thing. Again, assuming B is small, we've got, yep, only DF weights instead of This is compute bound, same thing. So a lot lower, meaning if we do int 8 weight quantization, which is fairly easy to do, but still do B15 floating point ops, we get meaningful win efficiency, though int 8 ops would be better. Let's see, what are they comparing to? This, right? When B is less than 240, no. So I don't care about that. What I care about is this. So when when B is greater than 240 tokens, we start to become compute bound. Whereas in this, if B is greater than 120 tokens. So it's funny. You're more efficient when you do when you use BF16, but that's only because the communication bytes is increasing. It's not like you're really using less compute, it's just the ratio of compute to communication is better. So it's like you're like allowed to use more memory with the same compute or the same setup. All right, anyway, let's do question 3. That was a quick one. Question 3. Let's see. Taking the setup from question 2, make a roofline plot of peak flops per second versus B for F equals D 4096 and F equals D 1024. Exact number of bytes loaded, not an approximation. Cool. So let's think about this a little bit before I start drawing. So arithmetic intensity on a log scale, flops per second. Accelerator peak flops. Okay, so that should be what, 1.97 E14? Yeah. Let's just draw our box first. Let's do bang, bang. Maybe go a little bit longer. Let's do here. .97 E14 up there. Arithmetic intensity, flops per second. So what do we really want to draw here? Flops per second versus B. So this is B. So let's say arithmetic intensity is a function of B. Let's just write it out fully so it's not confusing what my notation is. As a function of B, and then flops per second. All right. So how exactly should we graph this? So we need to have a line or a boundary or something when we become compute bound. So when B exceeds 120 tokens, or really when our equation for arithmetic intensity exceeds that. It's not so simple. So maybe arithmetic intensity as a function of b isn't really what we should be saying. We can fix that later. Roofline peak plot versus b. Oh, f and d are known. Okay, so that changes everything. So so scenario 1, so we'll do dotted line for this scenario, and then we'll do a straight line for this scenario. Let's write that here first. Let's do it a little bit higher so that it's easier to see. Line equals is f equals d equals 4096, and then this will be f equals d equals 1024. So maybe we want to do our calculation somewhere too. So intensity of matrix multiplication for f equals d equals 4096 equals, what was that again? It was 2 BDF divided by 2 BDF. Man, that's a long. Okay. 2 BDF divided by, what's it? 2 BDDF. 2BD plus DF plus 2BF. 2BF. Instead of writing the full thing out little by little, let's just go on Desmos here. Let's do 2 times, so DF equals 4096 squared, 496 squared. Let's also do 2 times 4096. That'll be our coefficient for BD here. And then for DF, it's also 4096 squared. And for that's the same value, so we should really have 4 times 8192b. So let's do that now. So 2 times 1092 squared. I guess we're going to write this full number out. So we're like, okay, so 33 million. So 33,554,432b divided by 2d is 8,192. Oh, but we're combining those, so 4d will be there eventually. So first of all, let's just do answer times 2. Cool. Yeah, let's put that first. So 6,384b plus then we need this. Wait, did I mess up? No. We want the thing squared, but not times 2. So let's just do this again. 4,092 squared plus 16,777,216. Cool. We could probably do like polynomial division to get this in terms of something easier to work with. So we can get it into like the polynomial expansion, a power series out of that. Let me just think for a couple seconds longer. So yeah, this should be a number along here. So this is the intensity. So what we want to know is at what point does this equal our TPU intensity. And there's a second thing here. Oh yeah, so there's two different lines for two different scenarios. Okay, so algorithm 1. So this equals a number. Oh, so we don't really care about the actual dotted lines algorithms here. We just care about these borders. So yeah, so we have one bandwidth here. We've got one. Oh, we got two algorithms. So let's see. So we know intensity of TPU is 240. So we can put that wherever we like on here. Let me just think. So if we put 240 here, so is the bandwidth a function of something? Because why does this increase with arithmetic intensity? I mean, I guess we really don't care so much about that line. We really just care about the regions. What I'm going to do here is just calculate the actual numbers first. So when does this equal 240? Right? Intensity, mats, mole, F equals D equals 4096 equals intensity TPU. So that's where we become compute bound in this scenario. That's kind of what they're asking for, right? Because we're looking at, yeah, when you're compute bound versus when you're not. So we are compute bound when this exceeds that. So we want yeah, okay, so set these equal to each other. So 3, 3, 5, 5, 4, 4, 3, 2, B divided by 16,384B plus 16,777 to 16 equals 240. So multiply that over minus that. Should be pretty easy, right? Okay, so 16, okay, so this, so answer times, actually, let's just do the full thing. No, let's not. Answer times 240 So this times 240 equals, let's first put an equal sign here, 3, 3, 5, 5, 4, 4, 3, 2, B. Make this a little clearer so the little tech thing can see it. Equals, well, just for the sake of order, let's do 16, 3, 8, 4. Whatever. 16, 3, 8, 4 times 240 equals that. We should probably also put this in scientific notation too. Let's say that's approximately 4 e to the 1, 2, 3, 4, 5, 6. Well, that's right? Maybe my scientific notation's wrong. Let's see. 4 times 10 to the 6. Yeah, okay, cool. 4, let's say approximately 4 e to the 6. Times b, right, plus 4 e to the 9. 4e9. Subtract, so what is this approximately? It's like 3 point, did you say, no, 3.36? I mean, the sig figs are all off, but I mean, we'll get close to the number, I guess. Yeah, let's just round to 1 sig fig. So let's just say 3 e to the 1, 2, 3, 4, 5, 6, 7. Oh, wait. Shouldn't that be one more than this? Oh, maybe not. Yeah, because this is getting much bigger. So 7. Let's see what it looks like. 4 to the 7. Yeah, 40 million. Okay, cool. So that's 4 e to 7 minus 4 e to 6b. So that minus 4 times 10 to the 6 should just be, is that right? Let's check out the actual numbers just to be certain. 3, 3, 5, 5, 4, 4, 3, 2 minus, it's this number, right? Minus 4.026 times 10 to the 9. Oh, this is the wrong. Oh, no, it's not. Did I do something wrong? There's no way. Oh, it's, yeah, no, it's 4 e to the 6. What am I doing? I think it's this number, right? 16, 3, 8, 4. Yeah, it's this number. Let's just use this. Bang. Bang. Okay, so it's 3 e to the, what is that, 7? 3 times 10 to the 7. Yeah. It's 3 e to the 7. Is that the same thing that we got earlier? Well, that's actually slightly different. But this number should be more accurate. So, okay. 3e7b equals 4e9. Man, these sig figs are probably going to kill me. We'll see when we get to the answer. I can already feel it getting messy. E7 B divide. So 4 e to the 9 is really 240 times this. So it's this number. So let's go here. This number divided by, well, it should be the same thing. 4 e to the 9 times, or divided by this, right? 135.9. Let's just round it to 136. B is approximately equal to 136. What's the units on these? I guess tokens. So we put this at 136. So we want one here and one here, right? Before we write anything down, let's see how this changes things so we know where to put what. So flipping over, that's right. Question 3, continued. That's right. Intensity, mat mole, F equals D equals 1024. Intensity, mat mole, F equals D equals 1096, 24. 1024 equals 2BDF DF divided by, should be 2BD 2DF, or no, DF plus BF. BD plus DF plus 2BF. Let's just check, make sure I got that right. 2BD, DF, 2BF. Cool. Now, next thing is putting in the actual numbers here. So the intensity of matrix multiplication changes now. Let's do, so 2 times 1024 squared. 1024 squared equals 2,097,000. 152B divided by 2 times 1024, 2048. So it really should be 4 times that. So times 2. Oh, whoops. Answer times 2, 4097. So it should be 4097B. It's the same thing, right? Just check to make sure. Same thing we did here. Yep. So that number is way smaller though. I wonder if I made a mistake earlier. Because 4 times 4096 should be around 16,000. And then 4 times 1024. Yeah, okay, it's just a lot different. Alright, 4096B plus DF is just 1024 squared. It's a big number. 1,048,576. All right, then we know. Let me just copy the same thing. Order at, yeah, I mean, it's the same thing. Let's just write it down again. Border at intensity matrix multiplication F equals D equals 1024 equals intensity of TPU. So it's 2,097,152B divided by 4,096B plus 1,048,576 equals, and then this should not be changed, 240, right? Yep. Cool. So again, multiply over 2,097,152B equals, so this number times, answer times 240, and then also 4,000, 96 times 240, 983040 B plus this number 251658 240, subtract, so this number how did I get that number again in the first place? Yeah, 2 BDF, so it should be 1024 squared times 2. Yeah, okay, good. This divided by no, it should be minus this minus this $1 million 1 E, what is that, 7? 1 times 10 to the 7. Nope, it's 6. It's 6 figures. 1E6 B equals 251,658,240. Subdivision. This, whoops, divided by this. Ah, shoot, I forgot to put it in there. Okay. What is it? It's this number. No, it's the big number. This. Divided by this. It's 226. B is approximately equal to 226. All right, so we got 136 and we got 226. I did not say anything about log scales, so I'm sure we can be fine doing this. Okay, so 4096 is a straight line. So let's do that. And then that's 136. Oh, whoops. And we got 226 for the other scenario. $226. So in this region, if we're less than 136 tokens, we're not compute bound for either. For either, what do they call it? Matrix scenario? What do they call it? For either, sure, let's say scenario. And then we can say compute bound for F equals D equals 4096, but not for F equals D equals 1024. And we can say both scenarios are compute bound. So we got that major part. The other thing in the diagram, I'm wondering about. So they only really give us one bandwidth, I think. There should be something here. Gotta think for a little bit. BW. Where's BW2? We could just draw an arbitrary line that goes. I should start at 0 though, right? Flops per second. So the arithmetic intensity is 0, which means that we're not doing any floating ops. It kind of should be 0. So are bandwidth 1 and 2 corresponding to algorithm 1 and 2? That is my question. I think at this point, I'm just going to consult the answer, see what they say here. Uh-oh. That was very different. So they're actually peak flops per second on TPU. So before we keep reading, maybe I can figure out how to replicate that. Okay, let me just check again. Yeah, the start was 0. Okay, that's what I thought. Thing is, so we want to get floating ops per second as a function of arithmetic intensity. Floating ops per second, or floating ops, is in the arithmetic intensity definition. We could just free ball it, but I'm pretty sure they have an actual. Yeah, they actually put it in here. Let's see what they did. Okay, range from 1 512. Roofline total flops time was total flops divided by. Okay, comms time, total time, turn total flops divided by total time. Both models eventually achieved the peak hardware flops per second, but the larger D over F achieved it sooner. Almost doubles the critical batch size. The code to generate this figure is guess a roofline big. So we're running a roofline on these, turning total flops divided by total time. I'm just gonna freehand it, honestly. Yeah, well, we'll see if that is sufficient. For now, I think we should take a break and then return later to do questions 4 and 5. And then we move on to the next section. Let's got a preview here. I think about TPUs. I enjoy section on NVIDIA GPUs. Let's see again, sections. So there's 12 sections, but I remember, I think the first 3 sections are kind of just like foundation. I said this was the part 2 that's really important. Training llama, inference serving llama, and this is like a extra. Well, let's see what the beginning says. They say here, I remember I didn't really understand this, but it looks like that'll be in the TPU section. Yeah, okay. Wait a second. Yeah, okay. And then part 2 is about transformers. Okay, so that'll get you through part 8. So that is the core practice tutorials. Interesting. Conclusions and bonus content. Gotcha. So the real stuff is in part 2. Alright, well, let's take a break and then we will get back to it soon in about 15 to 30 minutes. Catch y'all then.